Hi everybody, welcome to another video in Calculus 3, section 17.5, Divergence and Curl. On this section, we focus on derivatives of multivariable function. Right. Before we start our section, let's review something we already know. We define a gradient of a vector by define a del operator. So a del operator, it is a vector. So I could make this a vector operation. So it has three components, or we can just write. The first component is derivative with respect to x, the second one with respect to y, and the third one with respect to z. Of course, that can be defined on a vector field of two variables and two components, vectors in R2 as well. Now, gradient. Let f be a function with continuous partial derivative. Then the gradient of a function is defined as that. So pretty much we have a product of a del operator and a function. This is just a regular product or the scalar function. Right. So this should be easy. Compute the gradients for the following functions. So we have the function like that. We just find the partial derivative. So the gradient of a function f is equal to del f. Like I said, you might write this as a vector or just flip the upside down triangle. That works just fine. Right. So we have just that, or we can just spell it out directly like what we have here. So the del operator is that vector. So the gradient is the vector of partial derivative. This function only has two variables, so we only have the gradient is also a two-dimensional vector. Right, so just find the derivative with respect to x. Derivative with respect to x. This is a product of two functions of x. So derivative using the product rule be 2x. Product rule u prime v plus u v prime. So derivative the first one with the second plus the first with derivative of the second. Derivative of cosine xy is negative sine of xy. And then the chain rule say we have to take derivative of the inside with respect to x, which is y. So we have 2x cosine xy, and that minus x squared y sine of xy. Right, so that's what we have. And then the partial derivative with respect to y, we just have a function of y. Xy is constant, and the derivative of cosine xy is negative sine of xy, and then the derivative inside with respect to y is x. So we have negative x cubed of sine xy. And we just put in here. So the gradient is equal to 2x cosine xy minus x squared y sine of xy. That partial derivative with respect to x and partial derivative with respect to y is this. So that is the gradient of f. Now we have the function of 3 variables. So the gradient is the vector of partial derivative. You can just write like this. Yeah, so I just switch up the notation. Right, derivative with respect to x, that should be easy. 3x squared. Derivative with respect to y, derivative of e to the y is still e to the y, and we still have the constant z. And derivative with respect to z is negative e to the y. So that's all we do. Yeah. So the gradient is the vector of a partial derivatives. A gradient of a function is the vector of partial derivatives. Of course, we already know that. It's just a review. Now, we define a divergence of a vector field. A divergence of a vector field f of 3 components. That is differentiable on a region of R3. So this is a vector field in R3. The divergence is a dot product of a del operator with the vector field itself. So a dot product, the first with the first, the second with the second, and the third with the third. So this is a dot product. As opposed to here, the gradient is just a regular product. I mean the scalar. F is the scalar function times the vector. So that is the scalar multiplication. This is the dot product. And if the dot product is equal, if the divergence of a vector field is equal to 0, then the vector field is said to be source free. And because it is a dot product, this is going to be a scalar function. So whatever we have is a scalar function. Right. Divergence measures the expansion or contraction of a vector field at each point. If the divergence is equal to 0 at all the point, then the vector field is source free on that region. Now just compute the divergence of this vector field. So pretty straightforward. So we write the divergence of a vector field. Divergence is a dot product of a del operator with the vector field. The del operator is partial derivative with respect to x, y. Partial derivative with respect to y and partial derivative with respect to z. Now this is a dot product with the vector field f has 3 components, f, g, and h. So the first with the first. You don't have to write this every single time. Just know that this is a sum of the partial derivative. This is g, f, g, and h, dz. So this, I should just say, put x, y, z here, but derivative of f and h equal to z. Derivative of f with respect to x is 1. Derivative of g with respect to y is 1. Derivative of h with respect to z is 1. So this is equal to 3. So pretty straightforward. Now let's find the divergence of this vector field. So divergence of a vector field is a dot product of a del operator and the vector field. The del operator derivative with respect to x, with respect to y, with respect to z. And dot product with the vector field negative y, x, and z. I could choose a more complicated example, but just want to make things simple here. So derivative with respect to x, derivative with respect to x of x with respect to y, and derivative with respect to z, derivative of z with respect to z. So what do we have here? Derivative of negative y with respect to x, that's 0. Derivative of x with respect to y, that's also 0. And derivative of z with respect to z is 1. So we have 1. Next we find the divergence of this vector field. It's the dot product of a del operator. Keep doing that. And then the vector field negative y, z, and x. So I have derivative of negative y with respect to x, derivative of z with respect to y, and derivative of z with respect to x, and that is 0, and that is 0, and that is also 0. So if the divergence is equal to a 0 number, then this is said to be sort-free. So because it's just go around, so think about this. This vector field just pointing out on every direction like this. That certainly it has a source. Whereas if this is a rotational, so if it just go around, so there's no source. So that's the reason they name that way. But right, at this point we just worry about the calculation here. Very straightforward. Next, a curve of a vector field. So the curve of a vector field, this should be a vector field that is differentiable on the region of R3. So the curve is, this time we define for a function of 3 variables, and this is a vector in R3. The curve is a cross product of a del operator and the vector field. So the cross product we use 3 by 3 determinant, where the first row is ijk, and then we do the cross product. Because we talk about cross product, it should not be the problem. The three-dimensional curve of the vector field is a vector in 3 dimensions. So the curve is of a vector is also a vector. Right. Compute the curve of the following vector field. So we have this example. So a curve of a vector field is a cross product of a del operator with a vector field. A cross product. The first row ijk, the second row is the del operator. So derivative with respect to x, with respect to y, and with respect to z. And then the vector field f has 3 components. Right. So it's just normal cross product. So first one, for I, we will do cover the row and the column containing I. So that's pretty much that. Right. So derivative of z to z with respect to y. derivative of 2z with respect to y. Maybe I should write derivative. That is, if I'm going to write that, it's not going to be enough space here. So let's continue in the next line. So we have derivative of 2z with respect to y minus derivative 3xy with respect to z. That in the I component plus minus, sorry. Next one we cover the row and column that contain in I. So we have derivative of 2z with respect to x, subtract derivative with respect to z of x squared plus y squared, and then plus derivative 3xy with respect to x, subtract derivative with respect to y of x squared y squared. Right. So that is 0 minus 0 in direction of I minus that is 0, that is also 0, and that derivative of 3xy, so this is the only one that is not 0. I mean those two in the k, sorry, this in the j and this in the k, and that will be derivative with respect to x of 3xy is 3y, derivative of x squared y squared with respect to y is 2y. So we have 3y minus 2y, just a y, right? So we just have y times the k vector, or we will write 0, 0, and y as a triangular bracket. Right, that's simple enough, really straightforward. Next, we find the curve of this vector. I, j, k, and then partial derivative with respect to x, with respect to y, with respect to z. Vector field f, y squared, y, x plus z. Right, simple enough. That derivative of xz with respect to y, x plus z with respect to y, minus derivative of z, derivative of y with respect to z in the I component, minus derivative of x plus z with respect to x, minus derivative of y squared with respect to z in the j component. So this is minus, and then plus derivative of y with respect to x, minus derivative of y squared with respect to y. Right. So in this case we have derivative of xz with respect to y, that is 0 minus 0 in the I direction. In the j direction, this is derivative with respect to x is 1. With respect to y, z, y squared, derivative of that is 0. And finally, derivative of that with respect to y with respect to x is 0. And derivative of y squared with respect to y is 2y. So we just have 3 components, 0 first component, negative 1 for the second, and negative 2y for the third component. Right. Of course, we can write an ijk component, or we can just write in the triangular bracket. That's what I use here. Right. So pretty straightforward. Next, before we go to a theorem, we will prove this important result. Let f be a function, and f is a vector field of 3 components. Show that the curve of the gradient of a vector field is equal to a 0 vector, or we're going to write like that. And then the second one will prove the divergence of a curve is equal to 0. So this is a 0 vector, this is a 0 number. So we just need to distinguish that. Alright, first, the curve of the gradient of a vector of a function is equal to 0. So first I'll do the inside. The gradient of f is del f, partial derivative with respect to x, with respect to y, with respect to z of f. So we just have the vector of partial derivative. So simple enough. Next we'll calculate the curve of the gradient of f. The curve is the cross product between the del operator, and the gradient of f. So I have a cross product I, j, k. Partial derivative and then the gradient of f, f sub x, f sub y, f sub z. Right. Now for I component, we cross that out, and we will have, of course you can just write in terms of component. So component. Derivative of fz, f sub z with respect to y. So we have derivative of with respect to y of fz minus derivative with respect to z of fy. That's the first component. The second component, if we cover like this, notice that it's always negative. So derivative with respect to x of fz, f sub z minus derivative with respect to z of f sub x. Finally, derivative with respect to x of fy minus derivative with respect to y of fx. So those are 3 components. Put it together, we have f of derivative of with respect to z already. Now with respect to y, so this is derivative with respect to zy minus f of yz negative f of zx f of xz f of yx f of xy. Now, Claro theorem, we know the mixed partial derivative are equal, so zy, yz, xzx, xz, and yx, xy. So that's why we just have a zero vector, because all of them are zero, because mixed partial derivative are equal as long as we have the same combination. So we end up with a zero vector, just like what we expect. So, simple enough. Next, the divergence of a curve of a vector field is equal to 0. So first we'll calculate the curve of f. Curve of f is a cross product of del operator and vector field f. The del operator is a vector of partial derivatives operation. Vector field f is f, g, and h. Right. So when we do the curve, we will have to simplify things. I'm not going to skip a step, and I just said this is derivative of h with respect to y minus derivative of g with respect to z. The middle is negative derivative of h with respect to x and f with respect to z. Last one, derivative of g with respect to x minus derivative of f with respect to y. Right, I'll just take care of that negative sign. Hy minus g of z minus h of x plus f of z gx minus fy. So that is the curve. Now I will calculate the divergence of a curve of a vector field. Divergence is the dot product. Divergence is the dot product, and the curve is a cross product. So we have the del operator partial derivative, and then the curve we just calculate here, y, g of z, h of x, f of z, g of x, f of y. Right. Now pretty much we will take derivative of the first one with respect to x, of the second one with respect to y, and the third one with respect to z, and add all of them up. So derivative of this with respect to x, yx, zx, minus derivative of second one with respect to y, and the third one with respect to z. So we have x already, so that will be xz and then f of yz. Right, take a look. We have h of yx and h of xy. Those are equal because that mixed partial derivative are equal. G of x, zx, g of xz, that cancel out. And then f of zy minus f of yz. Those also equal. So everything cancel out and we have a zero number. So a curve of a gradient of a function is equal to zero vector divergence of a curve of a vector field is equal to a zero number. Right, so that's what we have a theorem here. Suppose that a vector field is conservative vector field. That means there is a potential function. In that case, we can write like this, and divergence of a gradient is equal to a zero vector. So a vector field that is conservative, then it is a gradient of some potential function. So if we have the curve of a divergence, the curve of a gradient, and that equal to zero vector. Yeah, so curve of gradient is a zero vector. That's exactly what we have earlier. Next, suppose vector field F is that where they have the second partial derivative, then the divergence of the curve is equal to zero. Right. We don't have this in the book, but at the higher, more advanced level, we will call the function is the zero form. The 3 form is also a function. So when we take derivative, the first step is the gradient, the second step is the curve, the third one is divergence. So we want 1, 2 step, we have a 0, and we go 2 step, and we have 0. So just not thinking about the gradient, the divergence, and the curve in terms of the separate operation. Just think of that, all of that, it's just an operator down. So we have 3 types of product. The first product is just a product of a vector and a number. So that's the scalar product, scalar multiplication. Divergence is a dot product, and the curve is a cross product. So think all of those 3 operators, all of 3 operations in terms of the operator delta, in terms of the operator del with a function on a vector field. Of course, if we have 2 vectors, we can have a dot product or a cross product. If we just have a vector and a number, a vector and scalar, if we can only have a scalar multiplication. So that is the gradient. Right. So this is a quick section. After this, we'll get back to the vector calculus, the integration. Right. I'm going to stop this section here. And as always, thank you for watching.